Hello, welcome to video problems for free fall and graphing motion. I'll start off with problem 1 on the video problem set. And this one is about throwing a stone upward. So let me read the problem. A stone is thrown upward vertically with a speed of 12 meters per second from the edge of the cliff of 70 meters high. We're going to figure out how much later does it reach the bottom of the cliff, what speed is it just before hitting, and what's the total distance. Okay, so we're throwing a stone off a cliff. So here's our cliff, here's our person. This is 70 meters tall, like this. So I'm going to label that. Here's our ground, just because. And then we're going to take this stone and we're going to throw it up at 12 meters per second. Those are the two numbers that they gave us in this problem, but as I discussed, anytime you have a free fall problem, including throwing upward, we can automatically assume the acceleration is 9.81. Since there is directional pieces, this object we know from just experience will go up and down. Because we have two directions, we must absolutely include this negative sign to ensure that the gravitation is acting downward, which it is in this case. So that's our additional information. From the problem, we technically have an initial velocity of 12 meters per second. And we have a distance here, so I may or may not use it depending on the what we're looking for. But the first part of the question says, how much later does it reach the bottom of the cliff? So just like I discussed, this thing is going to do a trajectory where it's going to go up some distance, which we don't know. Or maybe we can figure out. Then it's going to go down. Now, assuming this is something we can always assume that the up is going to equal the down. Since it's not being propelled in any way, it's just gravity that once it comes up, it's going to go down the same distance, at least at this point where it started. And then we have this distance right here, of course. And we know that value already as 70 meters. I'm just going to label this as some distance x, right? Well, let's use y since it's in the y direction. These are the same, so that's why I left them the same variable like this. How much later? So we're looking for time. So part A is how long, basically. Okay, to do the how long, the way I'm going to do is actually break it up almost like 3 parts here. I'm going to use what is called symmetry, and that's just a big word to say that I know whatever this does is going to be the same in terms of time. So if I know the time up, I'm going to know only this part though, time down. So once I figure out time here, I can double it. Then what I'm going to do is after I figure out the time of this area, I'm going to find the time of this. So notice that I'm breaking apart this problem. Just like most problems, it's best to piece it down into more manageable references. Now you could do this in one step. You could do the delta x equation, but the problem with this, although this is completely fine, is you have, a quadratic. And I don't like solving quadratics because what you have is you have to solve for t, but as you can see, you have t here, etc. So you can one-shot this with this equation. But it's actually really good to see the two, me breaking this apart because it's really helpful in seeing how these types of problems work. So I'm actually going to take a different approach. I'm actually, like I said, I'm going to solve just this half of the problem. And to show you what I can do with that is I have some information. Number one, I already have a velocity, initial. At the very top of the trajectory, I actually have that too. It stops ever so slightly. Well, not ever, it literally stops, but it stops very briefly. But I have that information. Then I have an acceleration. So even though this problem looks very vacant, I actually have a lot of information. So you can see right here that I actually have all the information to solve for time using this relationship. So I will plug in those numbers just like that. So as you can see, I'm using all the numbers I organized and solving for t. So I'm going to do that. I don't usually talk the algebra. I assume you're okay with it. So what I get is 1.22, I'm rounding seconds. But this is just for the up. So the up is 1.22 seconds. And then I can make the assumption, and it's okay, because I started and ended at the same spot, that this is 1.22 seconds. Now the beauty of also doing it this way is now I have some extra information for problems later if I need to solve additional parts like speeds, etc. So basically I have time 1, time 2, now I need the time down here. So I basically have most of my information. So I know, again from symmetry, is that if I'm going up at 12 meters per second, I'm definitely going to have the same speed over here, but my velocity, I don't know why I put that 0. The velocity is just negative because we're going down at this point. So you can imagine the ball right here, and it's actually going down. 12 up, 12 down. So we don't know the final velocity. In fact, that's an answer we're going to need later. We do have the distance this goes. So what I'm going to do to find this, and of course we always have A. These whole problems have A. So what I could do with this is actually, let's see, what did I want to do with this one? Let's see. I have this, I don't have that. Actually, what I'm going to do is actually solve part B to avoid, again, I'm avoiding the quadratic here. So actually, I'm going to take a shift over to B to get part A. So what I mean by that is actually, I'm going to find VF first, because I actually have all the information to do that. So I have the delta x, and I have A. So if you notice this equation right here, I can solve for VF, and then I'm going to use this equation to solve for time later. So why don't I do that? So VF squared is going to equal the initial, which is negative 12. Of course, that makes it positive in the end. Plus 2, negative 9.81. And notice that we're going a negative. If I'm starting here, this is my start point, my displacement's actually negative as well. So this becomes negative. So let me solve for velocity. So first I'm going to actually do all the algebra for this, and then once I do the algebra I have to square root it to get just v by itself. So I'm going to do 12 squared. Then I'm going to do the 2 times 9.81 times 70, and then square root that. So what I get is 38.95, and this is meters per second. So that's the velocity right here. So like I said, what I'm going to do is actually, now that I have that, I'm just going to scoot this down a little bit. So we have part B, so I'll just box this because we already have part B. Is now use this velocity with this equation. So I'm going to use this equation to find time. Again, it's a little roundabout because I am avoiding the quadratic, but it still works. So with the final velocity, this is negative. Let me just apply that in there because it's going down. And let's start from right here. My initial velocity is going to be negative 12. Now, if some of you see some shortcuts, can you just make these all positive? Yes, you can, but only if you understand that the signs work out in the end. It's best to just go with what's actually happening and not taking the shortcut. And I apologize that this thing is, coming in and out of focus. So solving for time here, 38.95. So I'm going to add, so it's negative, so negative 38.95. I'm going to add the 12 over, divide by 9.81. I get T is 2.75 seconds. So that's the time it takes to go this distance right here. Alright, so answering part A says what's the total time, and I will do that So basically I'm doing the first part plus the second plus the third times that I got. So that's going to be 1.22 seconds for the up. That's for this. 1.22 seconds for down, and then 2.75 for the rest of the down. Yeah, let's squeeze it in, 2.75 seconds. Again, some of you say, oh, I can just multiply that by 2 because they're the same. Yes, definitely take shortcuts if you see them. The final answer is 5.19 seconds, like that. That's for A. B, we did A and B. And then what is the total distance traveled? So part C. So why don't we actually, how do I want to do this? Maybe I'll extend the paper down to do part C. That's what I'll do. Part C. Okay, for the last part, what we're going to do is calculate the distance. So in order to figure that out, we need to just look at this one section right here. So by finding that one section right there, what we could do is apply reasoning that this distance here is the same distance here. And since we're adding distances, all we need to do is add this distance plus that distance to get the total distance. So first off, what we know is that the initial velocity we're going to use is 12. There we go. Sorry, my pen was a little weird. I don't know what's going on. Let's see. Come on, pen. Okay, I'm going to write over here because it seems a little more fluent. So let's do 12 meters per second as the initial velocity. The final velocity is 0. The acceleration is still 9.81. Like that. And our distance is what we're looking for, our x. So our equation is going to be vf squared equals vi squared plus 2ad, or delta x, as such. So I'm going to plug in our information. So our final velocity is 0. 12 meters per second. We're going to square that. Plus 2a, I'm running out of room, so I'm going to drop the units, x. So let me give myself a little more room here. I'm going to solve for delta x. So when I do, I'm going to do 12 squared plus 2 times 9.81. I'm sorry, 12 squared divided by 2 divided by 9.81. What I get for my distance is 7.34 meters, like that. So that is the distance up, 7.34 meters. We can assume that will be the distance down, since that's gravity is the only thing that's influencing this motion. The rest of this is 70. So now to find the total distance, I'm going to add the 3 values together. So delta x total is 3.74 plus 7.34, my apologies, plus the 70. To add those 3 numbers together, get 84.68 meters. And that's distance, not displacement. Displacement of the object would be negative 70, because if you notice in this problem, this is displacement. That we started at 70 meters above, or at least our height, as you can see, is 70. So that concludes video 3, number 1.